Hey everyone, my name is Teja, an MAT student from Xiamen University Malaysia. And today I'll be going over a topic from my MAT101 class called geometric sequences. In this video, I'll be covering 4 things. First is what are geometric sequences, what's a geometric series, what's the sum to infinity of a geometric series, and finally, what are its applications in real life, namely exponential growth. So first, what are geometric sequences? A geometric sequence is a sequence whose next term is a ratio of the previous, denoted by an plus 1 over an is equal to r, the common ratio of the sequence. So for example, if we have 1, 2, 4, 8, 16, and 32, each term is twice the previous. So we have, by our notation, that an plus 1 over an is equal to 2. So in general, for a first term a and the common ratio r, we have the formula an, the nth term of the sequence, is equal to a times r to the n minus 1, where r is real and not 0. If r is 0, then for any first term a, each next term is simply going to be 0, 0, and 0, and that's not really a geometric sequence. So let's take a look at some examples. So for this first one, 3, 12, 48, 192, by our formula, we have that an is equal to the first term 3 multiplied by the common ratio. So here, the common ratio is 4, because 3 times 4 is 12, 12 times 4 is 48, and so on. So we have an is equal to 3 times 4 to the n minus 1. For the next one, we have the first term 625, and each term is dividing the previous by 5. In other words, multiplying by 1 over 5. So we have that an is equal to 625 multiplied by 1 over 5 to the n minus 1. And finally, for the last term 1 minus 1, 1 minus 1, this is simply a first term of 1 and a common ratio of negative 1. Next, let's talk about a geometric series. A geometric series is the sum of all the terms of a geometric sequence, denoted by Sn is equal to a plus ar squared, all until ar to the n minus 1. Or it is the sum from k equals to 1 to n of ar to the k minus 1. So for this example, 1 plus 2 plus 4 plus 8 plus 16, the series, the sum, is equal to 31. In general, for a first term a common ratio r, and a sequence with n terms, the geometric series sum is denoted as a times r to the n minus 1 all over r minus 1. So how does one get this formula? Well, we first start with the general formula for the geometric series. We have Sn is equal to a plus ar squared, all until ar to the n minus 1. Now let's consider another series, Sn multiplied by r. So we have Rsn is equal to this entire series multiplied by r. So we have ar plus ar squared plus ar cubed, and so on until ar n, because ar n minus 1 times r is just ar to the n. Now let's subtract this series from the previous one. So we have Sn minus Rsn is equal to a, and if you notice, we can do a lot of cancellation. Ar minus ar is 0, ar squared minus ar squared is 0, and we can cancel all of the middle terms, and we end up with a minus ar to the n. Now let's start factorizing. On the left hand side, we can factor an Sn. On the right hand side, we can factor out an a. And we can divide both sides by 1 minus r. Now, if we multiply both sides, the top and bottom, by negative 1, this is equal to negative a 1 minus r to the n over negative 1 minus r. And if we distribute this, the minus inside the brackets, we have that this is equal to a rn minus 1 all over r minus 1, which is exactly our formula. Now let's apply this formula on these sequences. So for the first one, we know that Sn will be equal to the first term 3. The common ratio is 4 from our previous example, and this sequence has 4 terms, and divided by 4 minus 1. And we can plug all of this into our calculators. So for the next one, Sn is equal to the first term 625, the common ratio is 1 over 5, and we have 5 terms. And again, 1 over 5 minus 1. And the last one is also Sn is equal to the first term 1. The common ratio is minus 1, and this has 5 terms, all over minus 1 minus 1. Now, let's talk about the sum to infinity of a geometric series. The sum to infinity is simply the sum of a geometric sequence that has infinite terms, and this exists if and only if the common ratio r is between -1 and 1. Why? Because if the common ratio r is greater than 1, for example in this second example, 1 plus 2 plus 4 plus 8, each term is getting larger and larger and larger, and we add them up, it will always approach infinity. Whereas for the first example, 1 plus 1 half plus 1/4, each term is getting smaller and smaller and smaller, and if we take this sum term by term, we start with 1, 1.5, 1.75, 1.875, and we can see that this will slowly approach the value 2. So in general, for first term a and the common ratio r with the criteria that it is between -1 and 1, the sum to infinity is written as S infinity is equal to a over 1 minus r. And we can get this formula from our previous formula for the geometric series sum. So recall that we have Sn is equal to a Rn minus 1 over r minus 1. The sum to infinity is taking the limit of this sum as n goes to infinity. Now on the right hand side, only r to the n has the term n. So let's evaluate the limit as n approaches infinity of only that term. So as we can see, r is less than 1. So multiplying r by itself repeatedly will always make this value smaller and smaller and smaller. And doing this infinitely many times, this value will approach 0. So let's plug this into this formula. So we have that S infinity will be equal to a times 0 minus 1 over r minus 1. Negative a over r minus 1. Multiplying the top and bottom by -1, we get that a is over 1 minus r, which is exactly our formula here again. So now let's talk about its application, exponential growth. And for this, I'll be talking about compound interest, which is a system in which most banks calculate your interest. So in general, we have the formula a is equal to p times 1 plus r to the n, all to the power of nt, where a is the total amount, p is the principal or deposit, r is the interest rate, n is the number of times compounded per unit time, and t is our time, usually in years. So how is this related to geometric sequences and exponential growth? So we'll first take a look at this example. Calculate the interest earned per year from a 1,000 ringgit deposit compounded annually with an interest rate of 10%. So we'll first see in the first year, A1 is equal to the deposit 1,000 times 1 plus the rate 10%, which would be 0.1, over 1, because we're compounding this once per year, to the power of 1. And this is equal to 1,100. On the second year, A2, this is equal to 1,000, 1 plus 0.1 to the power of 2. And we'll get 1,210. In the third year, A3, we have 1,000 times 1 plus 0.1 to the power of 3, 1,331. Now let's take a look. On the first year, we gain 100 ringgit. And on the second year, we gain 1,110 ringgit. And on the third year, we gain 121 ringgit. As you can see, we're actually gaining more interest per year. And this is how it is related to exponential growth, where the longer we do this, the more we earn. And how is this related to geometric sequences? Well, let's take a look at A. A0 will be 1,000, A1 is 1,100, A2 is 1,210, A3 is 1,331. If we take a look, each term is 1.1 times the previous, which is actually exactly equal to the value inside our bracket, 1 plus 0.1. And that is how this is an application of geometric sequences. That's all for me. I hope from this video you can learn more about geometric sequences, a geometric series, and of course how it is applied in real life, namely in compound interest. Thank you for watching, and I hope you have a nice day.